In this mini lesson, we are going to talk about logarithms. So first, let's talk about what a logarithm is. In mathematics, a lot of times the same value or the same formula, and we just rearrange it in different ways or a different format. For example, 0.5 is the same thing as 1/2, but we have different ways of stating it. Same thing with formulas. When we have a formula for something, we can rearrange it for the different variables depending on what we're trying to solve for. So when we look at a logarithm, we need to recognize that a logarithm is an exponent. It's just written in a different way. So just keep that in mind. When we're talking about logarithms, the answer to whatever that expression is, where you're taking the log of something, that is an exponent. So let's walk through a couple of different examples. This right here that I underlined in green, this is a statement that's in exponential form. We know that 10 squared is equal to 100. We can write that in logarithmic form like this. So let me color code this for you. So the 10 here is the base. And whatever the base is, that's going to go right here. The exponent, which I covered up a little bit with my writing, let me erase it. The exponent is going to be your answer when we're writing it in logarithmic form. And then the answer, when we're looking at it in exponential form, is what's going to go inside the parentheses when you're taking the log of something. So I would say that 10 squared is equal to 100 is equivalent to log base 10 of 100 is equal to 2. Let's look at another example. The 4 here is my base. So that's going to be written right here. The 3 is my exponent. So that's going to be written as the answer to our log expression. And then when it's in exponential form, the answer is what's going to go inside the parentheses. So let's practice with these examples below and see if we can figure out what the answer is. And we're going to figure out what the answer is by writing it in exponential form. And that's going to help us understand it better because we're more familiar with exponents than we are with logs. So in this first example, it's saying the base is 6. The answer, when it's in exponential form, is 36. And this is saying, what's the exponent? So I would write this as 6 to what exponent would give me 36. So my exponent here is going to be 2. That's my answer here. So the log base 6 of 36 is equal to 2. Let's look at this one here. My base is 2. I'm trying to find the exponent. Let's write that down here. We're trying to find the exponent. 2 to what power gives me 16? When I take 2 to the 4th power, that's 16. So my answer to log base 2 of 16 is 4. Let's look at log base 10 of 1,000 now. So we're looking for the exponent. So my base is 10. So I'm saying 10 to what power is going to be equal to 1,000? Well, when I raise 10 to the 3rd power, that's what gives me 1,000. So in this case, my answer is 3. Looking at log base 5 of 625, if we're trying to find that answer, we're trying to find the exponent that goes with the 5 to get 625. So I would say 5 to what power gives me 625? That would give me an exponent of 4. Now these last two down at the bottom are special cases. So for log base 7 of 7, we're trying to find the exponent. So this would be 7 to what power is equal to 7? And of course, that would be 1. So this is a special case that when the base and what's inside the parentheses is the same thing, that answer for that log is always going to be 1. So last one, again, this is a special case. This is saying I want to find the exponent so that if I take 3 to some power, I'm going to get 1. Whenever you have a base raised to the exponent of 0, you are going to get 1. So this answer is going to be 0. This stems from exponent rules. So if you are curious as to why 3 to the 0 isn't 0 and why 3 to the 0 is equal to 1, you want to go back and look at your exponent rules about what you do to the exponents when you divide. So for example, if I had 5 to the third over 5 to the third, because the top and the bottom are equivalent, that's equal to 1. But if we use our exponent rules, when our bases are the same, we subtract our exponents. So I would have 5 to the power of 0 because I take 3 minus 3. So this is using our exponent rules. So anytime you're taking the log of 1, no matter what the base is, if you're finding the log of 1, it's going to be 0. So that's another special case. Now we got to talk about properties of logarithms because we're going to use those to solve some basic equations. We're leading up to being able to use logarithms to solve our equations. So a couple things to be aware of. If we have something called log base 10, that is called the common log. So when you see log base 10 of something, we'll call it just x for right now, this is called the common log. Now, sometimes that 10 isn't written in there. So sometimes you'll see it just written like this. When you don't see the base written, you assume that it's base 10, even if it's not written in there. Just like when we look at a variable and we have x plus 2x, that would give me 3x because even though it's not written in there, I assume that that's 1x. It's the same idea with logs. If there's nothing written for the base, you assume that it's base 10, and that's called the common log. Looking at the properties, if I have two individual logarithms, log of x and I'm adding log of y, I can rewrite that as one logarithm using multiplication. So whatever is here and here with the individual logs, we can combine it into one log with multiplication. And then you can do that in the reverse direction as well. If you have one log as two things being multiplied, you can separate the logs by putting a plus in between them. So the same idea goes for subtraction. If I have two logs that are separate, they're individual logs, whatever the first term is here, what's inside the log, right, that has to go on the top. And then the last property that we're going to talk about is this one here. This is called the power rule for logarithms. And whatever you're taking the log of is being raised to an exponent. You can take that exponent from here and write it down in front. All right, so now let's use the properties to expand and condense. We're going to practice using our properties here. When you see ln for a logarithm, that means it's the natural log. And that has a base of e. This e represents a number just like pi. It's an irrational number. Now, if I take the natural log of k divided by w, if we look back up here to our rules, let me erase now so that it's not so cluttered. Since we're looking at division, we want to look at this rule right here, rule number 2. And if you have the one log and inside the parentheses you have something divided by something else, you can rewrite it using subtraction with individual logs. So whatever's on the top goes first and whatever's on the bottom goes second. So I would write this as the natural log of k minus the natural log of w. This one has multiple properties that we can use. We have multiplication here and division. So looking at that division, let's start with that. Using the division rule, I can break that log up into two separate logs using subtraction. I take the top minus the bottom. So I would have log base 4 of 7. That's the top. And then I would have log base 4 of ma. Now, inside the parentheses, we have a product. So then we can continue to break that down and expand it using the multiplication rule. So using the multiplication rule, I'm going to rewrite this log of m times a as two separate logs. Now, one thing you have to remember that's a little bit tricky, if you have a subtraction and you're breaking this into separate logs, you have to remember to distribute that minus. So what you need to do is make sure you put parentheses around it so that you know that minus applies to everything inside. So I'm going to break that log up into two separate logs. So I have log base 4 of m plus log base 4 of a. And I used my multiplication rule right here, the first rule. Since I'm running out of room here, I'm going to rewrite it. Since that minus applies to log base 4 of m times a, which we just broke up into two separate logs, I have to remember to distribute that minus. So when I remove the parentheses and distribute the minus, we're going to have for our final answer log base 4 of 7 minus log base 4 of m minus log base 4 of a. For this one, log base 27 of 15 raised to the g plus 5, we can use the product rule here. Whenever you have a log and you're taking the log of something that has an exponent, that exponent can come down in front. Because that has two terms in the exponent, you want to make sure that you apply it to the logarithm, both of those terms. So the g plus 5 is the exponent so that it can come down in front. I'm going to purposely make a mistake here to show you what I mean. So I have g plus 5 that came down in front, then I have log base 27, and then I still have this 15. I just took the exponent and brought it down in front. Now, when I write it out like this without parentheses, it only looks like the log base 27 of 15 is being multiplied by 5. But remember, this whole thing was the exponent. Everything needs to be multiplied by log base 27 of 15. So if you pull something out of the exponent and bring it down in front, and it has more than one term in it, remember, both of those terms get multiplied by log of 27 base 15. All right, this next one is really easy compared to what we just did. For this one, we have the natural log of g raised to the power of m. Using the power rule, I can just bring that m right down in front. So my answer would be m times the natural log of g. Now let's look at log base 3 of 1/9 minus 5 times the log base 3 of 3. When you are condensing and you're trying to put it into one logarithm using the properties, you first want to make sure that if you have any coefficients in front of the log, that you work in reverse and bring them back up as an exponent. So you want to first rewrite this as log of 1/9 minus log base 3 of 3, and then I would bring that 5 that's in front of the log back up as the exponent. Now we have no coefficients in front, and we have two logs that are being subtracted. I have log of, oops, I forgot my base here. I have log base 3 of 1/9 minus log base 3 of 3 to the 5th. Because of this minus, we're going to change it into division. I have two separate logs, and I can rewrite it with division because I have a minus there. So I'm going to rewrite this as log base 3. The first value is going to go on top because with subtraction, the order matters. And then what goes on the bottom is 3 to the 5th. And then you can simplify that and take 1/9 divided by 3/5 and figure out what that is. That would give you 1/2187. A next example here, we don't have any coefficients in front of the logs that we have to worry about pulling up into the exponent. So we can go directly to writing this into one log. So since this is plus, I can write it as one log with multiplication. So I have log base 3, and then inside here, I would put y times y plus 3. If you want to simplify that, then you would just distribute the y. So your final answer would be y times y, which is y squared, and then y times 3 is 3y. Natural log of 55 minus the natural log of 11. There's no coefficients in front that I have to worry about pulling up before I try to condense. Because this is subtraction, I can just rewrite it as one log using division. This would go on the top, this would go on the bottom. So I would have natural log of 55 over 11. And we can simplify that as natural log of 5, because 55 divided by 11 is 5. Okay, last example here. If we want to expand this, we can use the power rule and bring the -3 down in front. So I have -3 times the log base 4 of a. So now that we practiced some of our properties, let's now apply that to solving some very basic exponential equations. Now, an exponential equation is when you have the variable that you're trying to solve for in the exponent. So in this first example, 2 to the x is equal to 10. This is considered an exponential equation because the x, what we're trying to solve for, is in the exponent. When you want to solve equations like this, I have some steps written out for you. The first step is to isolate the exponential part of the equation. When you're looking at the exponential part, that is the part where you have the base, just the base raised to the exponent, and everything else is on the other side of the equal sign. So in this first example, the exponential part is already isolated. So step 2, you can take the log of both sides. You can do anything you want to an equation as long as you do the same thing to both sides. So if I have 2 to the x is equal to 10, I can take the log of both sides. Let me move this over. So now we have log of 2 to the x is equal to log base 10. So now that we took the log of both sides, we can use the properties of logarithms to solve for the x. Using the power rule, I know that I can bring that x down in front. So now, the only thing left to do is to divide both sides by log of 2. This is what you need to put on your calculator to find the final answer. One thing I want to point out that's very important when you look at log base 2, these are not two separate things. This is one item together. You cannot separate it. So in other words, you can't divide both sides by just log or both sides by just 2. Look to see how we can enter our answers on the calculator. So you want to make sure you expand this. You can click on the keyboard down here so that your palette opens up. And you'll see down here we have the natural log, we have the common log, which is log base 10, and then we have a log here where you can put in your own base. So when you click on the log where you can put your own base in, you'll see that when it comes up on the input bar, that the cursor will be blinking where you want to put your base. In the case of this first example, we're using the common log, so that's going to be base 10. So you could either put it in yourself or you could use this log that's already set up. It doesn't matter. We got log of 10 over log of 2. So I'm going to put in log 10, and then I'm going to divide by log 2. So then I have to put in log 10, and then I'm going to put 2 in there. You cannot write this as log base 10 of 5 and combine the 10 and the 2 by saying 10 divided by 2. It doesn't work that way. You can't cross off the logs and then have 10 over 2 left with 5. That doesn't work like that. So make sure you type it in exactly how you solved it. So the answer is going to be 3.3219, and then you just go out as far as you need to for rounding. Let's look at this next example. I have 10 to the power of x plus 1 is equal to 1,000. So when you look at this, My exponential part for step number 1 is already isolated. I have my base raised to an exponent and everything else is on the other side. So I can go to step 2 and I can take the log of both sides. So I'm going to put a log in front of both of these numbers. Now, because we have it written with logs, I can use the properties of logs. So I can bring that x plus 1 down in front. Now remember, x plus 1 is the entire exponent, so you want to make sure you put parentheses around the x plus 1. So it doesn't look like you're only multiplying one of those terms by log. You want to make sure you're multiplying both of those terms by the log. So it's going to look like this. So now I have x plus 1 times log of 10 is equal to log of 1,000. We can go ahead and keep solving. So in order to solve for x, I need to distribute. So I'm going to take log of 10. So think about that as a number, and you're just distributing it to everything that's on the inside. So we have x log 10, because you take x times log 10, and then you're distributing the log 10 to the 1. So I have 1 times log 10, which is just log 10. And then on the other side, we can just leave it as log 1,000. Now, you want to get the x by itself now. We finished step 3 where we used the power rule to bring the exponent down. Now we have to solve for the x. You would subtract the log 10 to the other side and then divide by log 10. So you would have x is equal to log 1,000 minus log 10, because you take the log 10 and subtract it to both sides, and then all you're left with is x times log 10, so then you would just divide both sides by log 10. We put that in the calculator and find our value. We got the answer of log of 1,000 minus log of 10 in the numerator, and then we divided by log 10. I'm just going to use this button here so I don't have to keep typing in my own base. And I'm going to put log of 1,000 minus log of 10. Now I'm going to purposely make a mistake here. I'm going to divide by log of 10. Now this here is not what we solved for. When we solved this, we got log of 1,000 minus log of 10 all in the numerator, and then divide by log 10. Now, it's coincidental that it came out to the right value, but this is not correct. To make sure that that doesn't happen where you're only dividing these two, you want to make sure that the log of 1,000 is in the numerator. Let me start over. You want to put parentheses on what you want in the numerator. So I'm going to put log of 1,000 minus log of 10. So that's the numerator. It's all in parentheses. Then when I divide, it's all going to stay in the numerator. Then I can do log of 10. Looking at this next example, I have 2 raised to the power of 3x minus 1 is equal to 10. Here, you have your exponential part of the equation isolated. So we don't have to worry about step 1. It's already isolated. I see my base with my exponent on one side and everything else on the other. So now what I can do, step number 2, is take the log of both sides. So I take the log of 2 raised to the 3x minus 1 is equal to log 10. Now I can bring my exponent down in front, remembering to put parentheses around that because we're taking the entire exponent, multiplying it by log 2. And now I have to distribute my log. Remember, this is just a number. Log 2 is a number, and we need to distribute it. So I have 3x log 2, because I took log 2 times 3x, minus, now I take log 2 times 1. That's log 2 is equal to log 10. So now I have to do step 4. We just did step 3 where we used the power rule to bring the exponent down in front, and now I have to solve for x. I want to get the x term by itself, so I'm going to add log 2 to both sides. So I have log 10 plus log 2. Then I need to divide both sides by 3 log 2 so that I can get x by itself. So my answer, once I cross off the log 2's and the 3, I'm going to get x is equal to this right here. And then we can put that in the calculator and get a value. We have the answer to be log 10 plus log 2 all in the numerator, and then divide by 3 times log 2. So because we have multiple terms in the numerator, I want to make sure I put parentheses so that the GeoGebra knows that it's all in the numerator. So I'm going to do log 10 plus log 2, and then I'm going to divide by 3 times log of 2. So our answer in decimal format, for example 3, is 1.4406, and then you round it as you need. Last one, I have a 2 minus 10 to the x. I want this 10 to the x to be completely by itself. So what I need to do is I need to subtract 2 to both sides. So I get negative 28 and a minus 2, that gives me a negative 30. Then I can divide both sides by negative 1. And when I divide both sides by negative, it makes both sides positive. So I have 10 to the x is equal to 30. Now I have the exponential part isolated, just like I did in the other 3 examples. Now I can go from there. I'm going to take log of both sides. So I have log 10 to the x is equal to log of 30. So I can bring the x down in front, and that will leave me with x times log 10 is equal to log 30. And to solve for x, I have to divide both sides by log 10. So these disappear, and I get that x is equal to log 30 over log 10. So I have to put that in on the calculator. This is a good example of where you might want to start canceling things that you shouldn't be canceling. Remember, the log of 30, those go together, you can't separate them. And the log of 10 goes together, you can't separate them. So I cannot cross off the logs and be left with 30 over 10 and then reduce it as 3. You cannot do that. The log and the 30 and the log and the 10, those go together. You cannot break them up. Let's go over to the calculator and find our decimal value for that. So let's put in our answer here and see what it looks like in decimal format. Log of 30, and I'm going to divide by log of 10. So my answer in decimal format is going to be 1.47712, and then you just round as the direction asks you to round. So let me show you how you can enter logarithms in the answer text box. For this one here, the question says we need to expand this and write it as the sum or difference of logarithms. Here we have the natural log of 2x. When we multiply and we want to break it up into 2 separate logarithms, multiplication means we're going to separate it with a plus in between. So when I go click on this text box to enter my answer, I'm going to choose this menu here that says functions. And then you'll see in the palette we have 3 different logs. This one is the common log, where it's assumed to be base 10 even though we don't write it in there. This one is the natural log. And then this one is log where you can enter any base that you need. Because in this example here, we're using natural log, and I use the same log, so I'm going to separate the 2 and the x by creating 2 different logarithms with an addition in between. So I'm going to write this as natural log of 2 plus, then I'm going to choose natural log again, so the natural log of x. And I can submit. There you go. Let's do one more. So in this example here, we're going to use the power rule to bring that -4 down in front. Notice here we have a log base 5. When I click on the answer box, I'm going to choose functions. Because this is base 5, I want to choose this log here where I can enter my own base. This is base 10. This is the natural log, so I need to choose this one. When it comes up, I have the cursor blinking down here where I can put my base. To come up from out of that subscript, I'm just going to use my right arrow key and it will pop back up. And then I'm going to put in log base 5 of x. And now, because I need to pull that -4 down in front, I'm going to arrow over and put in my -4. Now I have it entered the way I want. I'm going to hit enter. So that's how you want to enter your expressions if you're dealing with logs.